Yeah. So, hi all. Good evening and welcome back to the ninth week of TA live sessions for AI SMPS. I hope my audio is clear and my screen is visible. Can someone just confirm it quickly? Okay. Thanks for confirming. I hope it's audible to all. If not, please let me know. So today we'll be discussing some questions from week 9 content of the course, which will be discussing more of planning algorithms. We studied some of the planning algorithms like FSSP, BSSP and cold stack planning in the previous live session, and this week we'll be talking more about graph plan, okay, and some other methods like AO star as well. So without further delay, I think we can get started. So we'll be working with the same problem domain that we discussed at length in the previous live session. We still have the same predicates, wherein we have three individuals, Amol, Aisha and Anisa, and based on a set of initial facts about these three people, we have to choose among different operators and arrive at an optimal plan for these individuals. Okay, and these are some of the predicates given to us that convey different information to us for any general person who can be named X or called by the letter X. Okay, so I'm not going to repeat again because I hope people would be familiar with the problem statement when we discussed it last week. So these were the predicates, and these were the six operators that we would be dealing with that relate to several different tasks that we might want to do while we are planning the algorithm or while we are developing the plan using the algorithm. Okay, and these are the two states. The left hand side is the initial state where we are given several facts about the three individuals, and then the right hand side is the goal state where we are given the three predicates or three facts that we want to achieve with respect to each individual. Okay, so this is the problem setting, and what the first question tells us is from the given options below, we have to select the actions that will be present in the first layer of the planning graph that will be constructed by the graph plan algorithm. Okay, so first of all, how many of you are familiar with the graph plan algorithm? You might have come across the same in the lecture videos. Okay, if not, let's go over the algorithm very briefly so that you get an intuition about what we have to do exactly over here. Okay, so let's list all the facts that we have in the initial state for easy reference to us. Okay, so we are given that we have no jab Aisha, that is Aisha doesn't have any dose or jab of vaccine. Okay, we are also told that Anisa has one jab. And we are told that Amol has two jabs of vaccine. And we are told that Aisha is at the hospital and Aisha has a hospital appointment as well. Okay, so this is the initial state given to us. Let's mark it as initial state, and these are essentially a set of predicates, right? We will call this as P0. Okay, so this whole collection of uh, facts together or predicates together, we will call it P0. Okay, and next what we will try to do is we will try to develop an action layer, which we will call A1. Okay, so in graph plan we will have alternate layers of predicates like this one, followed by some action layer where we will add several actions that we could perform given the previous predicate state. Okay, and then this will be followed by another predicate state which we will call, sorry about that, P1. Okay, and then this will continue. We will again form A2, then form P2, and so on and so forth until we reach a situation where the predicate state contains all the facts that are present in our goal state. So we have achieved all the goals that we want, all the sub goals that we wanted to achieve in the goal state have been satisfied already or have become true. That, or we have reached a stage where we cannot add any more predicates no matter how many actions we perform. Okay, so these are the two ways in which we can stop our graph plan algorithm, but there are some nuances to it, to how we add actions and how we connect the different predicates to the elements in the action layer, and how we connect the elements in the action layer to the elements in the predicate layer. Okay, I hope most of you are familiar with the forward state space planning algorithm that we discussed last week. Can I just get a hand raise for those of you who remember? Anyone? Okay, thanks for confirming. I hope others are also familiar. So we'll follow a strategy very similar to what we did in forward state space planning. Okay, so there what we did, we were at a given state and we saw which are the different actions that we could perform using different permutations and combinations of the facts given to us. We will do something similar over here. The difference is there are some additional nuances like I was telling. So one of those nuances is the concept of a no-op. Okay, so suppose we simply want to carry forward a particular fact from predicate state P0 to P1. Okay, we can develop our own operator, call it no-op. Okay, which will have its precondition as the fact that we want to copy. Okay, and the positive effect of that predicate will be the same predicate. Okay, so this is an example of the no-op operator that adds this fact no jab Aisha straight from P0 to P1. Okay, this yellow marked operator is called a no-op operator. Okay, I have marked it with yellow, you can mark it with any other color. This is just for your understanding. Okay, this yellow edge between the predicate and the operator, this marks the prerequisites for that operator, and the blue edge marks the positive effects of that particular operator. Okay, so you can carry forward as many facts as you want from one layer to another as long as it adds value to your graph plan algorithm. Okay, or it makes sense to your graph plan algorithm. Okay, so this is one nuance. Then let's consider something that we did generally in the forward state space planning algorithm. Okay, so let's consider Amol's task, which was Amol wanting to attend the concert. Okay, and you are told that Amol has 2 jabs of vaccine. Okay, so let's see which are the operators we could apply for Amol. So Amol has two jabs of vaccine. So Amol can book a ticket for this particular event, right? That is one thing that Amol can do. So let's make that. So Amol can use this particular prerequisite. Okay, let's add over here. So I'm not writing the whole thing. It's basically book tickets for the event. Okay, so this is the operator, and let's see what are the positive effects of this operator. Okay, so the positive effect of this operator is that there will be a fact ticket for the event that will get added to our next predicate state, but there are no negative effects. Okay, so we got saved. Let's draw our positive effect in the next predicate state, and that would be ticket for that particular event. Okay, again I'm not completing the whole thing, but you can get the idea and complete it whenever you are trying to solve this problem again on your own. Okay, so this was another example of how we can add operators. Okay, now let's consider an example. Okay, let's focus on Amol itself. Let's see what are the other operators that we can add. Okay, so remember, get appointment is also one such operator that we can add, right? Because it doesn't have any pre-requirements. It only has a positive effect and no negative effects. Okay, so we can add that as well to our graph plan. So get appointment for Amol. Okay, again this does not have any prerequisite, but this has a positive effect, which would be Amol has a hospital appointment. Okay, similarly, what are the different uh, elements in this action layer? What are the different actions that we could add in this A1 layer for Anisa and Aisha? Okay, so for Amol we added all the actions that we could add. What about Anisa and Aisha? So this is also straight from the last week's discussion. So does anyone remember what we did there? Okay, so just for a refresher, let's consider Anisa's goal alone. Okay, so Anisa, we are given that has one jab of vaccine. Okay, so based on this fact alone, which are the different operators that we could apply for Anisa? We can apply the get appointment operator, right? Because none of the other uh, operators over here are exactly fitting in with the precondition or the fact given to us. Okay, all of them require additional pre-requirements, or their pre-requirements are different from the facts that is given to us regarding Anisa. Okay, so the only thing we can add is get appointment Anisa. So let's add that. Okay, and this also has a positive effect, which is that Anisa now has a hospital appointment. Okay, is there anything else that we can add for Anisa? Uh-huh. Mm-hmm. Yeah, the prerequisite is she should be, yeah, at the hospital and having an hospital appointment. So at any given time when we want to apply an operator, we want to have all the prerequisites with us for us to be able to apply it. Okay, so yeah, thanks for your question. I hope that clears it up. So I think we finished whatever operators we could apply for Anisa. What about Aisha? So we are given three facts about Aisha. I'll go back to the initial state. Okay, we are told that we are told that Aisha has no jab, Aisha is at the hospital, and Aisha has a hospital appointment as well. We can definitely add another get appointment, because just like we saw in case of Amol and Anisa, this does not require any prerequisite. Okay, so this will again have a positive effect. Okay, now let's go back and see whether there's something else that we can apply. Okay, so let's look at this get jab one. Okay, so this prerequisites for this operator are that X doesn't have any jab of vaccine, X is X is having a hospital appointment, and X is at the hospital. All these three are correct or applicable in case of Aisha, right? So we can apply our get jab one operator. So let's add that to our action layer. Okay, so this is another operator or action that we added, but this now has prerequisites. So let's connect the prerequisites. So one of them was Aisha has no jab of vaccine, then Aisha has a hospital appointment, and then Aisha is at the hospital herself. Okay, so these are the three prerequisites, and this had some positive effects as well. Let's see that. The positive effect is that Aisha now has one jab of vaccine. Let's add the positive effect as well. Okay, let's mark it with a blue color. This was a positive effect, but there are also some negative effects of this operator. Okay, which are, let me use it as a red color, that once Aisha gets the first jab of vaccine, all these facts that Aisha has no jab, Aisha is at the hospital, and Aisha is having hospital appointment, these three become nullified, right? So these are the negative effects. So let's draw edges that depict these negative edges. Okay, so one negative effect of this action is that this part becomes untrue. Okay, no jab Aisha is now not true. Another part that is falsified is that Aisha does not have a hospital appointment anymore, and Aisha is not at the hospital anymore. Okay, I am not adding everything over here. Maybe once we complete the whole action layer, we can add all the other negative edges as well. But this is an example to show you how we exactly add negative edges. Okay, now as long as there is no conflict between a positive edge effect and a negative edges effect, we are fine. But the moment there is a clash, for example something like this, right, here we see that no jab Aisha is a negative effect of this operator or this action, get jab 1, whereas no jab Aisha is the positive effect of a different operator, which is this no op operator. If such a situation arises, then we say that these two operators, this one and this one, which lead to a contradiction, they are mutex or mutually exclusive, in the sense that if we decide to include both of those actions together at the same point of time in our plan, they would lead to they would lead to effects that would contradict each other. Okay, so let us designate that by this zigzag line between the two operators. Okay, so this was one example of mutex operations. What I would like you to do is try to complete this action layer and see if there is anything else that we can add, and if there are any more mutex pairs of or mutually exclusive pairs of operators that could be present in this A1 action layer. Okay, and consequently we can also fill up our P1 layer. So I'll let you try to solve this for maybe 2-3 minutes, and then we can discuss the solution as well and complete the P0, A1 and P1 layers. Okay, So I'll leave it on here for 2 minutes while I just go and get some water. Okay, so I am back now. Were there any questions while I was gone? Please feel free to unmute yourself and speak up if there were any doubts till now. Anyone? Okay, that's great then, if there are no doubts. So let's look at the complete set of these P0, A1 and P1 that I have already made, and let's see if how many of those we were able to cover. Okay, so maybe I'll zoom in a bit. Okay, so this is P0. Okay, the middle one is A1. Okay, and the right hand side is P1. Okay, so we added get jab 1 Aisha. Okay, we didn't add go Aisha to the hospital, right? Yeah, so that was left, but we could add that. The prerequisites for that would be as specified by the operators given to us, which is hospital appointment Aisha. Okay, and the positive effect of that would be that Aisha is at the hospital. Okay, similarly, we added get appointment Amol, we added get appointment Anisa, we added get appointment Aisha, we also added book Amol comma concert. Okay, so this is the only action that we are yet to add, except some of the no op operators. Okay, so we added some no op operators as well, and we saw that there are some more pairs of mutually exclusive operators in the A1 layer or the action 1 layer. Okay, and these happen to be get jab 1. Let me show it with the laser pointer. This is one such operator that is mutually exclusive with this no op operation, okay, which we I think just saw, which is because this one leads to a negative effect of Aisha having no jab of vaccine, whereas this no op operator leads to a positive effect of Aisha having no jab of vaccine. Okay. Similarly, this get jab 1 Aisha and get appointment Aisha are also mutually exclusive, because get appointment Aisha has a positive effect of Aisha having a hospital appointment, whereas get jab 1 Aisha has a negative effect of hospital appointment Aisha becoming untrue. Okay, so these are some of the contradictions that we see, and hence we realize that these several pairs of operators are mutually exclusive. Okay, so I've given a legend over here where the zigzag line is essentially demarcating the mutex actions. The blue lines indicates the positive effects, the red lines indicate the negative effects, the yellow lines indicate the preconditions, and this special operator over here designated by a yellowish square or rectangle having an incoming yellow prerequisite edge and an outgoing positive edge demarcates a no op action. Okay, so I'll leave it on here for a while so that you can convince yourselves of the validity of this partial solution. So we have still not completed the whole plan. Okay, we are still maybe halfway through through solving the plan, but these are some of the initial steps that we have to take when we employ the graph plan algorithm. Okay, so I'll let this on here for maybe a minute, and please feel free to let me know if there's any confusion in this question till now. Hi, yeah, please go ahead. I think I have covered all of them, but yeah, yeah, yeah. I think I had when I had prepared this. I think I had covered all of them, but we can verify. I will also encourage all of the attendees to. Yeah, yeah, that's uh-huh. Mm-hmm. So when I was describing it over here, I marked only one of them. Yeah, but in this one, I think we have one, two, three, four, and five of them. Uh, just but still, for being on the safe side, I would encourage everyone to just go through it once and see if I have missed out on any of the mutex pair of actions. Uh-huh. Mm-hmm. Mm-hmm. Okay. Mm-hmm. Yeah, I agree. So this process, this graph plan algorithm can get very tedious if we have to draw the whole plan in one go. So usually what will happen is either the goals that will be given to us will be independent of each other. For example, the one that we are dealing with currently, right? So here we saw that we can build Amol's plan, Anisa's plan, and Aisha's plan separately, right? From last week's session, I hope you remember. Yeah. So if that is the situation where we know that the three are independent of each other or three or more of them, then we don't need to focus on drawing the plan for each one of those agents. We can just focus on one agent and then draw a sparse version of the graph plan algorithm that will have slightly fewer edges and connections. But if they are not independent, they are dependent on each other, then we have no other option. We have to adopt a strategy. uh, I will also show you the complete graph plan figure that was provided by Bhaskaran sir for this question, and you will soon realize that it is quite complicated and tedious to do in one go, especially manually. So what I have usually experienced till now is that you will be asked questions related to specific parts of the graph plan algorithm. So maybe the practice assignment gave such an open-ended question. I haven't looked at it, but maybe it was open-ended so that you get a practice of solving the whole thing on your own. But it's likely that in the final exam or in the main assignment, uh, you won't be asked to solve the whole of it. I hope so. I'm not sure. So yeah, you can check it up. Mm-hmm. 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 Mutex link in. Sorry for interrupting you. Uh, all mutex link in any one particular action layer or all possible action layers? So yeah, so that is similar to what we are doing currently, right? We are only. Uh-huh. I think 10 is a relatively small number. So yeah, I think your approach is thorough, so that will clearly give you a final result of which of them are mutually exclusive and which of them are not. But if you want to, I'm not sure if this is really like a shortcut or such. But if you draw these color-coded lines, like I have drawn over here, uh, then you can just look at which of these edges are having a contradiction of color in the P1 layer, right? So for example, this blue and red are having a contradiction over here, right? So this means that whichever source this blue line and red line are coming from, they are likely to be mutex because they are contradicting each other. So this is something that you can think of as a shortcut, but yeah, not really. Depends on perspective, I would say. Yeah. Mm-hmm. That I don't remember. I have to revisit the. Yeah, I have to revisit the lecture slides to see what exactly those four conditions were. But I can give you an overall idea. When we say these are mutually exclusive, we mean we want to convey the thought that we cannot have these two occurring together. So if I have to talk in terms of the set theory, which we may have come across in our earlier education, so these are two sets, right? And these have some intersections. So we can't say that these two are mutually exclusive of each other. But if there are two such sets which do not have any intersection, we say that those are. Yeah, yeah. So this is. Yeah, so that is analogous, but then yeah, I would like you said, I would recommend that you check the four conditions as you mentioned about when to and when not to classify a pair of actions as mutually exclusive or not. But yeah, this is like an intuitive understanding. uh, can you tell me which slide is this part of? Oh, it's in week 8. I see. Yeah. So it says that two actions A and B are mutex if one of the following holds competing needs. There exist propositions such that PA, which is a prerequisite of A, and PAB says that is the prerequisite of B, such that PA and PB are mutex in the preceding layer. Aha, okay. So what this essentially wants to convey is that if in the predicate layer itself we have two such predicates that are contradicting each other, then the corresponding operators that they will be connected to, they will also be competing, right? For example, let's say there is one fact given in the predicate layer or predicate or the proposition layer that says that Aisha has no jab of vaccine, and let's say there is another fact or another predicate or another proposition in the same layer that says Aisha has one jab of vaccine. Okay, so these two are contradicting each other, right? So these two predicates themselves are mutually exclusive. So whenever we try to draw a corresponding action in the subsequent layer, whichever action or operator they will be connected to, they will also be at mutex with each other. Mm-hmm. Mm-hmm. Okay. Okay. Um, you can do that, but I would suggest you can take any approach that seems more intuitive to you. But I would say that this approach of just looking at the predicate themselves and see if they are contradicting each other would be easier, right? For example, if we take this hold C and on TC, so the first predicate says that the robot is having the holding the C block in its hand, right? And this one is saying that C is on the table. So these two can't be true at the same time, right? C would be either in the hand or on the table, right? So it both can't be true together. So whenever we see such a pair that would have like contradictions that would negate each other, then that will be mutex, yeah. But you can look into the theoretical explanation of it and try to solve it that way as well, whichever seems more comfortable for you. Okay, in this example itself. Okay, so practice one, you'll have to look into it. I haven't seen that. So it can't be mutex with itself, right? So we need a pair. Which practice assignment are you referring to? In this one? Which of the following are applicable? Okay. Okay. I guess you'll for put down D, the preconditions are holding only. Okay. So uh-huh. Okay, so do we have holding what is this? Hold put down D. So we should have holding D in the prerequisite, right? Do we have that? We don't have that, right? In layer 1. So here do we have, okay, we have holding D. Yeah, so yeah, we can have put down D. Yeah, whether we can have the others or not as well, that we'll have to check, I think. Check, compare with each of the prerequisites and see if they are occurring in the layer 1. Does that make sense? Okay. Mm-hmm. Mm-hmm. Uh-huh. I would suggest for understanding, for so there are two steps, right? First step is to understand what we are doing. Where to understand, use whichever method seems convenient to you. You can use a tab, you can use a paper. Once you are comfortable, okay, uh, then you can try to make yourself adjusted to the kind of environment you will be situated in or placed in during the examination. So if we don't have access to tabs in the examination, we only have paper, then you can practice and make yourself more familiar with that kind of an environment. Okay. So there's a question in the chat box. What is the decomposition counting? Is this related to this course? Which week? Okay. Where exactly is it? Can you point me to it? Okay, week 9 in the lecture materials. Okay. Ah, okay. This is related to the AO star method, is it? Uh-huh. Okay. So we have a few questions related to this AO star application as well, and hopefully when we discuss it, it should clear up some of the doubts. But if it doesn't, then we can have a more in-depth discussion on that. Does that sound good? As in, we have some questions related to that AO star method in the material for today. Okay, so let's get back to the question that we had. I already showed the answer, but I guess you would have also solved it by now. So it basically asked us which are the actions that will be part of the first layer in the planning graph. Okay, and we just saw that it would be get jab 1, get appointment Aisha, go Aisha to the hospital, get appointment Amol, book Amol concert, and get appointment Anisa. Okay, these are the few actions that would be part of the first action layer in the graph plan algorithm. I hope there are no doubts here. The second question tells us what is the number of actions not counting the no up actions in the plan produced by graph plan. Okay, so this is actually related to what we did in the previous week. Okay, so before I do that, I'll just like to show you the complete graph that we have so that you get an idea of the scale. Okay, so this is available to us thanks to Bhaskaran sir. Okay, and this is the graph plan, the complete graph plan for Amol. Okay, so Amol, only Amol. Okay, and you can look at it at your leisure time. It is placed in the same folder where all the other lecture slides or all the other live session slides for the Monday live sessions are kept. Okay, and you can see that the mutex relations are marked with this dotted red line, whereas the negative effects are marked with this uh, thorough red line. Okay, so we just drew the graph till P0, A1 and P1, but there will be A2, P2, A3 up until P4 eventually, when we will have this attending Amol comma concert finally over here. Okay, or it is present over here as well, but you'll have to see which of these are giving us an optimal plan. Okay, so you can look at your own time. Similarly, we have this for Anisa, so you can see the scale is increasing as we are having to deal with more possible options, okay, or more possible branchings. And this is the graph plan for Aisha. This is even more tedious to construct. Okay, so yeah, you can verify this whole thing at your own time, but for now let's go back to the question that we had. and remember the optimal plan that we discussed in the previous live session. Yeah, so if in case someone doesn't remember, these are the three optimal plans for the three optimal plans for the three agents. Okay, so for Amol it required two actions. For Anisa it required 1 2 3 4 5 of them, and for Aisha the optimal plan was made up of 6 actions, right? 1 2 3 4 5 6. Okay, so the total number of actions to go from our initial state to the goal state, which consisted of all of these agents having their goal satisfied, would be how much? That's right, we'll just add up all of them. So 2 plus 5 plus 7, 2 plus 5 plus 6, that gives us 13. Okay, this is the total number of actions, not counting the no-op actions, in the overall plan produced by graph plan. So graph plan will also produce the optimal plan. Okay, going to the next question, what is the make span of the plan produced by graph plan? So is anyone familiar with what a make span is? So make span is essentially what is the maximum number of options, or not options, operations that you have to perform in order for your plan to be fulfilled completely. Okay, so you could think of it in terms of the three agents that we have. Okay, so although Amol's plan will be finished in 2 operations itself, Anisa's plan will be finished in 5 operations itself, we have to apply at least 6 operations in order for our plan to be completely fulfilled, right? So the maximum of 2 5 and 6, which is 6, this would be the make span of the plan produced by our graph plan algorithm. Okay, does that make sense? Uh-huh. Not the minimum, you have to think of how many maximum, how many of these operations that you have to perform so that all others are also fulfilled in between while we perform all of this. That's why we took a maximum of 2 5 and 6. Do the change in the order of actions affect optimal plan? Depends on what kind of change you are making. If it's a sequentially dependent set of actions, then yeah, it would be affected. If it's independent, then it doesn't matter. Okay, so that ends our discussion on graph plan, and now let's go to the AO star or and or graph method. Okay, okay, let's go over the problem statement given to us. Okay, the given figure below is an and or graph. Okay, so and or here basically refers to the type of branching that we have. Okay, so here you see that the S node with a value of 37, that has 3 possible directions we could proceed in. We could go in the A direction, okay, which is this one, the left one. We could go in the D direction, which is the right one, and then there is a middle direction which is consisting of B and C that are connected by this small curved line. Okay, so whenever this line is present, that means that both B and C have to be solved together for us to be able to solve S. Okay, this is essentially an example of how a problem can be decomposed. So this brings us to the query about the decomposition that was raised by Hina in the chat box. Okay, so assume that there is a problem S, okay, and this can be decomposed and transformed into one or more simpler problems. Okay, so for example, S can be decomposed either into A or D or B and C that need to be solved together. Okay, each node has a given name, and the number is basically a heuristic estimate of the cost required to solve that node. Okay, remember the cost given in the node is the estimate of the cost required to solve that node, not the exact cost, except if it's a double layer, if it's a double circle or concentric circles present in a particular node, that represents a primitive node or a node that has already been solved, in which case the cost given inside that particular node would be the actual cost. Okay, so this is the problem statement. Is there any doubt in the problem statement before we move on to the solution of the following? Okay, that's great then. Thanks for confirming. So now what we have to do, or what we can do, is assume different edge weights. Okay, let's assume that each edge in this graph has only one unit cost. Okay, which basically means that if we are at say A, okay, going from A to S requires us the cost of A, or the heuristic cost of A, plus the edge cost connecting A to S. So if the edge cost between A and S is 1, then the cost of S would become 31 plus 1, which is 32. Okay, let me draw it so that it's clearer. So let's say this is as cost 1, this has cost 1, this has cost 1, this has cost 1. Okay, so we have three possible scenarios, right? This is S. We could go in the A direction. Okay, A has cost 31, and if this has cost 1, S would be having a cost of 31 plus 1, 32. Another possibility is that we go in the B and C direction, but the catch here is that we have to solve both B and C to be able to solve S, right? B has a cost of 25, let me write that beside this, and C has a cost of 20. Remember, heuristic cost, not solved because B and C are not solved yet, and these edges have cost 1 1 each. So the cost of solving S would be 25 plus 1 plus 1 plus 20. How much is that? That would be 47, right? Please correct me if I am making any mistake. Okay, another possibility is that we could go in the D direction. Okay, and D has a heuristic cost of 37. If we do plus 1, that would give us 38, right? And we want to have the minimum cost for S, for solving S, right? So which of these options do you think would be beneficial for us to pursue? Yeah, that's right. Thanks for your answer. So this A direction looks more promising. So let's draw a mark it with this direction. So we were going in this direction. Okay, let me erase the rest of these. Also, if you might have observed, there is particular situation happening with the estimated heuristic costs and the actual cost that we have found till now. I'm not saying that the actual cost is the correct cost that we have found till now, but just based on the fact that we have expanded node S, or explored which of the directions which would be beneficial from S, if we consider this 31 to be the true value, if we assume that A had actually 31 cost, the cost of S would become 32, which is less than the estimate of S that we had, which is 37. So what does that tell us about whether we are overestimating or underestimating when we are using the heuristic value? That's right. Thanks for the answer. Yes, so according to this observation, it seems like we are overestimating the heuristic cost. But let's proceed and see whether this gives us any fruitful results or not. Okay, so like we did for S, now we will expand A, or look into which options we could go to from A. Okay, so A has two options, E and F. Okay, F is solved with cost 38, E is not yet solved with heuristic cost 30. So assuming this also has weight 1 and this also has weight 1, the cost if we go from in the E direction would be 30 plus 1. So this will A will remain 31, and then S will remain 31 plus 1, 32. Okay, whereas if we go in the F direction, A will become 38 plus 1, 39, right? And consequently S will become 39 plus 1, which is 40, right? Which is greater than what we have currently. So we don't want to go in the F direction, we will go in the E direction. Does that make sense? Okay, that's great. Then now let's see which direction to go from E. So here we have two options L and M. Both have solved nodes, okay, and M has cost 25, and assuming these two also have weights 1, so we will prefer to go in the M direction, right? So 25 plus 1 would make E as 26. 26 plus 1 would make A 27, and 27 plus 1 would make S 28. Okay, so this is the solution that we arrived at by following this SAEM direction. Okay, but is this the optimal decomposition? Is there some path that will give us a value even smaller than 28? That's right. If we go in this direction, let me show it with a different color. If we go in this direction, we will see that we get a cost lesser than 28. How? Let's see. So this is 12 plus 1, so this will change from 17 to 13, right? So the cost of D now becomes 13 plus 1 for this edge plus 10 for K plus 1 for this edge. So how much is that? 13 plus 10 is 23 plus 2 25. So D becomes 25, and then S becomes 25 plus 1 26, right? So had we gone in the S, D, JK and N direction, then we would have an even lesser cost for solving the problem S, but we didn't get that. Why so? Because our heuristic value had overestimated the cost. Okay, if we underestimate, we know that our AO star algorithm is admissible, and if it's overestimating, it's not admissible. For why that is so, you can revisit the lecture slides and the lecture videos. I think Professor Kimani would have gone through that. But for now, let's see what would happen if we underestimate. Okay, so no, we didn't get right, because we got a value 28, which is higher than what we would have gotten had we taken a different path. If it's a small tree, yes, it's easy to verify manually. If it's a large tree, then we have to rely on our method like AO star. Okay, and we have to hope that heuristic value being used is underestimating, so that we get an optimal result. What do you mean by full solutions? So the decomposition defined by the graph given to us is the only information that we have. Like, we can't say that S will be decomposed into some other node that that is other than A, B, C and D, right? We can't say that S has another edge coming to some node Z that has a cost 2. So we can't assume that. So we just have to do whatever we can with the information that is given to us. Okay. 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 So for this, I am not exactly sure what is meant by full solution. If it means that how many optimal solutions are there, and in case there are multiple optimal solutions, it might be referring to that. If it means something else, then I would encourage you check with the lecture slides once, and if there is any specific definition of full solutions given over there. Okay, or if the question itself elaborates further on what is meant by full solution, that could also help. Okay, then maybe lecture slides might have some answer. Or you can actually, if while there is still time, you can even post in the discussion forum and say that there is an ambiguity in this question. What exactly is meant by full solution? That is something you can do as well. Mm-hmm. See, we can go in different directions, right? We can go in, yeah, but those are at the first level itself, right? At the first level, we have how many options? Three options, either A or D or B or C together, B and C together, right? Further down, we have further branching, right? So that gives us more options. So we chose to go in SAEM direction. We could have also gone in SAEL direction. That would have not given us an optimal solution, but that is also an option. Similarly, we could have also gone in the SAF direction. Yeah. Okay. Okay then. Um, so this is one question related to the assumption we made about the edge weights, which is 1 unit, and it basically asked us how um, we have to list the nodes in the order in which they were expanded by the AO star algorithm, and we saw that those were S, A, and E. Okay, and the cost associated at the different stages was 32, 32, and 28 as the different expansions. Okay, so this is just a follow-up question from the discussion we just had. Now let's okay, this question asked whether it's optimal or not, and we saw that it's not optimal. Now let's assume that each edge has cost 10 units, and let's try to solve it. Okay, so this is now 10, this is now 10, this is 10, and this is 10. Okay, so I'm not drawing the different options available to us at a given moment. Okay, I'm just noting that down. Okay, if we choose to go in the A direction, we would have 31 plus 10, 41. Okay, if we choose to go in the D direction, we would have 37 plus 10, which is 38. Oh, sorry, yeah, that would 38 would have been if it was 1. So this would be 47, and then if we go in the BC direction, we would be 25 plus 20 plus 20, that would be 65, right? So the most promising looking over here is the A direction, correct? So let's make those changes. Uh-huh. Mm-hmm. 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 Hmm. Yeah. If there was some other, if let's say this D instead of being 47, this was 32, we would have preferred to go via D. Yeah, yeah. Okay, so let's expand this. So this would, if we go in the A direction, this would become 41. Okay, so let's note down. First we expanded A. Okay, next we are looking to expand. Sorry, first we expanded S. Next we are looking to expand A. Okay, now A has two options, 30 and 38. These also have cost 10 each, right? So if we go in this direction, this would be 30 plus 10, which is A would become 40. Okay, and S would become 50, right? 40 plus 10, 50. But would that be beneficial when we already have a cost 47 if we go in the D direction? No, right? So this is basically what this is telling us is if we proceed, although if we look only one level further in the tree, in the decomposition tree that is given to us, or graph that is given to us, it seems that A is more promising. But if we go one level deeper, it seems that following the SAE path will give a cost of 52s, but we already have a cost of 47, which looks more promising if we go in the S to D direction. So we will switch our path, okay, and we will try to explore D next. Okay, and let's see what is happening over here. So in order to solve D, we need to solve both J and K, okay, and these have cost 10 and 10 each. So what would be the total cost? 17 plus 10, 27, plus 20, 47. So D would become 47, and then let's note that down, and then S would become 47 plus 10, 57, which is even higher than what we would have gotten had we gone in the SAE direction, right? So we will again switch back to the SAE direction, okay, and then we will expand E, and here we will see that again these edges have cost 10. So we will go with the M direction, of course, because this gives us lesser cost. So we will have 25 plus 10, which is 35 for E, then 35 plus 10, which is 45 for A, and finally 45 plus 10, which is 55 for S. So this would be our optimal decomposition, and these are the nodes that we would have inspected: S, A, D and E. Optimal because if you made an observation over here we are underestimating the cost. So when we explored the first level, right, we chose to go in the A direction, which gave us a cost of 41, whereas the heuristic value that we had was 37, which is less than the cost that we got, which is 41. So the heuristic function was underestimating, and we know that whenever such a situation happens, AO star is known to be admissible and known to produce optimal solution. Okay, so there's a question: if we get both values are equal, which node you will take? So to me it seems like in case both, if there are two directions that give us the same value, then we can choose to explore any one of them, selecting one of them randomly, and then see if exploring further gives us a better solution. If not, we will again switch back to the previous state, or previous approach, or previous direction. That is what it seems to me should be the case. But yeah, I will encourage you to verify it with the algorithm given in the lecture slides or in the notes shared by Bhaskaran sir, if he has provided any such thing. Okay, so this was the AO star method. Let's go back to the questions that we had. So we again have to repeat questions 4 to 6. So those were reporting the nodes visited, those would be S, A, D and E. The cost at each such expansion would be 41, 47, 50 and 55. And is this an optimal solution? Yes, it is. Okay, so these are the 4 questions that we had to answer. Sorry, 3 questions we had to answer. And this completes the discussion from AO star that we had for today. Okay, is there anything else that you would like to discuss? Otherwise we can disperse now and meet next week. Uh-huh. Solution for the assignment question? How to solve, I think, would be similar to what we did in the live session. Yeah, I mean, the setting might be different, but the approach would be same, right? But yeah, I don't have the full solution with me. Which question is this? 5? Okay. Okay. So BSSP, what did we do? We looked at the, see, how to proceed would be similar to what we did last time. We have to look at the goal condition. Okay, where is the goal condition over here? Okay, on C comma A, on B comma D. This is what is given to us. So in order to achieve that, we have to check which of the options available to us could be producing on C comma A or on B comma D. Okay, let's have a look at that. Yeah, so we have to basically go through the list of operators and see which of them could have a positive effects of having on something something, right? So we see that stack x comma y is having a positive effect. Is there anything else that is having a positive effect? No, only this one, right? So we will add this in the one penultimate layer of the BSSP tree that we would be forming, right? So the end node would be having on C comma I, on B comma D. One level above to on C comma I, on comma D, on B comma D would be stack C on top of A, stack B on top of D. These would be two further sub goals that would be added. Okay, then we will further see which of these sub goals could be fulfilled by which operator, and we will keep doing that until we reach the initial state given to us. Okay, it's a similar approach to what we followed the last time. um, I can try to solve this myself and present it again, but what would be even better is you try to solve, you or some of your friends try to solve it. No, doesn't matter if you have a full solution or not. Whatever partial solution you have, you post it in the discussion forum and say that I have solved it till this level. I am now confused at so and so point. How should I proceed? Okay, and in that situation, I think Bhaskaran sir would be able to pinpoint exactly where something is going wrong, or if everything is correct until now, and you should just proceed with the rest of the method. Okay. Uh-huh. Yeah, sure. Okay. Okay. Uh-huh. Mm-hmm. Mm-hmm. Mm. That's right. Mm-hmm. Mm-hmm. Yeah. Uh-huh. Mm-hmm. No, no. So the first three nodes would be SAD, because we add a node to the list of expanded nodes only when we expand it. So as of now we hadn't expanded E. We just saw that if we had gone in the A direction, we were actually looking to expand A here, right? So if we had gone in the E direction, we would have gotten 30 plus 10, 40 plus 10, 50. But we didn't expand E itself. We would have gotten 50, but that would be greater than 47. So we switched to D, and then we started expanding D. Okay. Okay, there's a question in the chat box. Repeat about the optimality for the graph. So basically, the thing is, whenever the heuristic value is underestimating, AO star is admissible and hence will produce an optimal solution. That is the one line that you would be good to, that would be good if you remember that. For more explanation, you can look into the lecture slides or the lecture videos. Yeah, there's a hand raise. Please go ahead. Okay, maybe it was by mistake. No worries. So, if there's nothing else, should we end the meeting now and convene again next week? Okay then. So yeah, thank you all for attending. Let's meet next week.